So I am Ness, and this is work with I am Meltzer-Asscher, and I'll talk about adaptation of prediction. In the past decades, a large body of research has provided strong indication that when we process sentences, we do not passively wait for the input and process it as it comes. Instead, we constantly engage in predicting the upcoming input. In this line of study of prediction in language processing, there are usually two aspects of predictability that are often operationalized. The close probability of a certain word and the constraint of the preceding context. So what we do is we use a sentence completion pretest. We give participants the beginning of a sentence or a phrase, and they need to provide the first completion that comes to mind. And from this data, we get two things. First, the close probability of a word is the proportion or percentage of participants who have provided this word as a completion. This value reflects how predictable the word is in this context. So in this example, the word dog has a close probability of 60%, and the word cat has 10% close probability. So dog is considered more predictable than cat. Additionally, we get something called constraint, which means how constraining the context is. So an attribute of the context and not the completion. And its value is the close probability of the most probable completion. This reflects the extent to which the context encourages a strong prediction. So for example, this sentence has a constraint of 60%, which is relatively high. But if, for example, the sentence talked about a farm where many other animals can be petted, then the close probability for the strongest option would be lower. So the sentence would be less constraining because there isn't any single highly probable word that we can predict. A vast amount of studies show that predictable words are easier to process. So a successful prediction facilitates processing. And recent studies have also looked at the costs of prediction failure when predictions are wrong. So looking at the processing of unpredictable words, research shows that their processing entails additional costs if the initially formed prediction was strong, relative to when no strong prediction was available in the first place. This is most commonly evidenced in the frontal post-N400 positivity, frontal PNP, which is an ERP component that is elicited by words with low close probability, so unexpected words, but only when they appear within a high constraint context, so only when there's this confirmation of a strong prediction. And we have recently argued that this prediction failure cost reflects inhibition of the falsely predicted word. So if the comprehender made a strong prediction about a specific word, and it is then disconfirmed, then they need to inhibit the wrong prediction in order to integrate the actual word. Additionally, previous studies also looked at adaptation of prediction in sentence processing, which means how comprehenders can change their prediction strategies from one situation to another. Most relevantly, Delany, Bush, and colleagues have shown that this adaptation can be formalized using a Bayesian adaptation model. What they did is they used ERP data from an experiment in which participants were presented related and unrelated prime target word pairs. And the proportion of related and unrelated pairs was manipulated between blocks. The common finding is that in related words, the prime word is predictive of the target word, causing facilitation for the processing of the target word. This is a very common finding. What this study specifically showed was that the proportion of related pairs, when the proportion of related pairs was higher, this facilitation, the priming effect, was greater. And the authors then showed that the trial-by-trial data fits a Bayesian adaptation model in which, after each trial, participants update their belief about the likelihood of a related pair. And this belief is used in order to weigh the relative influence of relatedness to the prime versus just the general word frequency. So participants base their predictions more on the prime when related pairs appear more often or are more likely to appear. Notably, previous studies of adaptation on prediction mainly focused on the predictability of the target word or on task demands and other factors that can affect prediction, but they do not specifically isolate the influence of constraint. And as we've seen in the frontal PNP studies, the processing of low clause words incurs additional processing costs in high constraint due to the need to inhibit this strongly predicted word that was disconfirmed. So in this study that I'll show today, we hypothesized that the disconfirmation of strong predictions should specifically be the target for adaptation rather than just any low clause word. Additionally, the target of these adaptation mechanisms should be to reduce the need of inhibition by avoiding strong predictions. So this adaptation should specifically influence the processing of high constraint contexts. So in the studies, in the experiments I'll show, where we specifically manipulated constraint, I will first go through the experimental design and a basic analysis, and then I'll detail our Bayesian model that we used. The materials consisted of two word phrases in which the first word is either highly constraining or not, but the second word was always a low clause completion. The materials for the first experiment were in Hebrew and for the second sentence in English, but this played no role here. So for convenience, I will use the example in English. So a high constraint, low clause probability phrase, which I will refer to as high constraint, low clause probability, would be, for example, rear view mirror. So after rear view, we can form a strong prediction for mirror, but then we get the congruent but unexpected word, camera. A low constraint, low clause probability phrase, low, would be, for example, vegetable soup. So soup is just as unpredictable here as camera in the previous example. But we don't have any strong prediction to form in the first place when we see vegetable. These two types of critical trials were presented in two lists that differed in the filler trials. So one list included high-low fillers, meaning that these participants encountered a high proportion of high-low phrases. And the other list included low-low fillers, meaning that these participants did not encounter many high-low phrases. So the proportion of disconfirmation of strong predictions was manipulated between participants. And our prediction was that in the high-low list, since participants repeatedly encountered the disconfirmation of strong predictions, they would start avoiding the formation of strong predictions, and therefore the cost of inhibition would decrease or even be eliminated. The two word phrases were presented word by word, and the task was to respond whether the phrase is congruent or not as quickly as possible once the second word appeared. So we had anomalous fillers included just to enable the task. So now for the results. We first did a mixed effects regression with the data of the critical trials with the factors trial type, list, and trial position throughout the experiment. There was a main effect of trial type, such that reaction times were indeed higher in the high-low trials when there should be inhibition of the wrong prediction. So these are the basic prediction failure costs. Importantly, there was also an interaction between trial type and list, such that this inhibition effect was smaller for participants in the high-low list, indicating that these participants, who encounter the disconfirmation of strong predictions more often, indeed avoid or alleviate the costs of inhibition, presumably by avoiding strong predictions. And I should also note that we expected to find a three-way interaction between trial type, list, and the trial's position in the experiment, which would have indicated that the decrease in the inhibition effect throughout the experiment occurred at a greater rate in the high-low list. But this interaction was not significant, which led us to think that maybe the adaptation in the high-low list just occurred too quickly. The proportion of high-low trials in this list was very high. And also there were no high constraint trials in which the predicted word actually does appear. So adaptation may have taken place prior to any or very few critical trials in this list. So what we wanted to do is to find a way to better account for the trial-by-trial dynamics of the adaptation process. And we therefore formulated a Bayesian adaptation model inspired by the Delany-Bush paper I discussed before. The idea is pretty simple. The participant repeatedly updates their belief about predictive validity, which is the probability that after a predictive first word, so a high constraint, the predicted word would actually appear. And this belief is then used to weigh the cost incurred by the prediction error in the subsequent trial. So as the participant learns that the predictive validity is low, the cost incurred by the prediction error would decrease, since the participant starts avoiding strong predictions, and therefore inhibition is less and less needed. Mu is a point estimate of the participant's current belief about predictive validity in each trial. It is simply the mean of a beta distribution, with the beta parameter increasing whenever a high-low trial is encountered, since this is when the participants should decrease their estimate of predictive validity. Prediction error is the difference between the expected close probability and the encountered close probability. So constraint minus the close probability of the presented word. And we multiply these two to get the inhibition index, which is the prediction error weighed by the participant's estimate of predictive validity. And it is the model's prediction of how strong should prediction failure costs be in each and every trial. And this inhibition index was calculated for each trial and entered into a regression model. This graph shows the calculated inhibition index, so the model's prediction. We can see that it is higher for high-low trials in red than for low-low trials in blue, since there isn't much of a prediction error in the low-low trials. We can also see that this inhibition index, of course, decreases as the experiment progresses, and more so for the high-low trials. And importantly, we see that the decrease is greater and faster in the high-low list on the left panel, since these participants experience the disconfirmation of strong predictions very often, and their estimate of predictive validity decreases rapidly. The results show that this inhibition index was a significant predictor of reaction times. The model outperformed alternative models, and this inhibition index was significant also when it was added to the basic model I described before, which included trial type, list, and trial position. In the experiment I just showed, the Bayesian adaptation model, as I've said, was conceived after we have already looked at the data and did the basic analysis that was planned. So the analysis with the Bayesian model was somewhat exploratory. We therefore did an additional experiment for which the Bayesian adaptation model was included in the pre-registered analysis. In this experiment, we also made some additional changes. First, in order to slow down the adaptation in the high-low list. And second, to extend the Bayesian adaptation model to also account for high constraint trials in which the predicted word does appear. So what we did was adding high trials, high constraint, high close probability. These are the results. I won't go into more details since the results are in line with the results I just showed in the previous experiment. But if anyone is interested, you can ask me about it later. So to conclude, the current study provides additional evidence for the costs associated specifically with the disconfirmation of strong predictions. It also provides additional evidence for adaptation of predictions during sentence processing. We additionally show that adaptation is exclusively triggered by low close words in high constraint, rather than just any low close word, and that this adaptation mainly affects the processing of subsequent high constraint trials. This indicates that participants learn to avoid strong predictions when such predictions are repeatedly disconfirmed in the current global context. And this adaptation can be formalized as a Bayesian adaptation model where participants iteratively update their belief about predictive validity in the global context, and then use this belief to weigh the strength of their subsequent predictions. I have a couple of future directions, but I think I'm out of time, so I'll skip it. And thank you so much.
Thank you, Tal. Any questions? I'll ask the questions while people warm up for it. What do you think will happen if you ran it in an ERP experiment, and would it even be informative more than the things you showed here?
Yeah, so in ERP, I guess what we would look at is probably the frontal PNP component. It should be in line with the behavioral results that, as the experiment progresses, I expect the amplitude of the frontal PNP to decrease because there's less inhibition. Yeah, so this would be the main thing. Additionally, something that I didn't go into, but we have a marker for, or we think we have a marker for commitment to strong prediction that we found in a couple of experiments we did. So this may be informative in seeing whether on the first word, we also start seeing a difference in the ERP, so that we actually see not only that the costs on the second word decrease, but also that participants commit less to the prediction when they see the first word already.
Okay, thank you. I see Inbal has a question.
Yeah, thank you for the talk. So one is a clarification. I think I just missed this. I was wondering how you obtained the constraint and clause probabilities. Like, was this only based on production, or did you use corpus data?
No,
so
this was based on clause probability pretest. In the English version, we created the materials based on a corpus, so we do know that there's also a high transitional probability there, but we mainly used the close production task to.
And so in that case, I kind of wonder why, like what's the justification for using that rather than confirming your expected and using an additional converging, hopefully, source of evidence from actual usage patterns? That's one question. And the second is how and whether you relate. So one literature that wasn't mentioned in the introduction is the one about syntactic adaptation, which is actually very similar and has used, to my knowledge, also similar Bayesian approaches to modeling this. So I'm wondering how that relates to your work and how do you see the connections or the differences?
Well, I guess I'm not sure I fully understood the first question, but I think the benefit of using clause responses rather than frequency in the corpus is first that corpuses in Hebrew are more limited than in other languages sometimes. So this was a preference of our, but also research has shown that frequency is not a better predictor of predictability in behavioral results. So a close probability probably encompasses additional things other than just the transitional probability between the first word and the second word. But I expected we would get very similar results if we were looking at corpus for that. And regarding the second question, I think that our adaptation of prediction abilities are kind of so far seem pretty unlimited. So it can take the form of adjusting our predictions of specific words, which is what we looked at here. And it can take the form of predictions of structure. We didn't specifically manipulate any grammatical adaptation, but yeah, so I think these are two probably.
I was just wondering how your models relate to existing models in the field of syntactic adaptation, because I agree that we probably do kind of predictions on various levels of analysis, and it's interesting to think whether there aren't differences in adaptation between them in the future. Thanks.